It may come as a surprise for some of you that the function in the previous example was not differentiable. We note that the function which is the absolute value of z square is just equal to x square plus y square. It has this as a real part and 0 as the imaginary part. And we note that the partial derivatives of this function u, the real part, they exist. But still the function f of z is not differentiable. Differentiability implies continuity, exactly as in the real case. So if a function is differentiable, it will also be continuous. The opposite is not the case. Here you have an example in the real case of a function which is continuous, but at this point it is not differentiable. We are going to consider some rules for the derivative. If we use the symbol, this symbol for the derivative of f at the point z, this is often used, d f of z over dz. Then we have that the derivative of a constant is always 0. This is exactly as in the real case. Moreover, the derivative of z with respect to itself is equal to 1. The derivative of a constant multiplied with a function f of z is always equal to the constant multiplied with the derivative of f. Moreover, we have, as in the real case, the derivative of a polynomial function. Derivative of z to the power of n is equal to n times z to the power of n minus 1, where n is some integer. If n is less than 0, then we have to assume that z is different from 0 in the point where we are considering the derivative. Well, if we take the derivative of a sum of two functions, then it does not come as a surprise for you that this is exactly the same as taking the sum of each of the derivatives. Similarly, for a product, the derivative of a product of two functions are equal to the product of, as in the real case, it is the derivative of the first function multiplied with the second function plus the derivative of the second function multiplied with the first. Exactly the same rules as in the real case. And also for the derivative of some fraction, if we have a differentiable function in the numerator and another in the denominator, we have this formula for the derivative of this fraction. Here we have to assume that f of z is different from 0. And the chain rule in the real case is exactly the same in the complex case. If you have a function which is a composition of two functions g and f, like this, then the chain rule tells us that the derivative of this function is the derivative of u at the point f of z multiplied with the derivative of f. So here is an example of this. If you have the function z2z square plus I to the power of 5, then we can, in this case, it's natural to let g in the chain rule be equal to u in to the power of 5. So, and we let this f of x be equal to 2z squared plus I. So then we just use the chain rule, take the derivative of g with respect to u first, and obtain 5u to the power of 4. And the derivative of f of z is just 4z. So the chain rule then tells us that the derivative of f at the point z is 5 u in 4, and you take the substitution u equal to this guy and multiply it with this, and you should have to the power of 4 here. Sorry that we have this misprint, so it should be to the power of 4 here multiplied with 4z. This is exactly as in the real case, which you have seen many times.